Hello everyone and welcome to my presentation on a non-parametric method to investigate non-Gaussianity in cosmic microwave background maps. My name is Sarvesh Kumar Yadav and this work is being presented at Cosmology from Moon 2025. Our research is motivated by a fundamental assumption in modern cosmology. The perturbations produced during inflation are thought to be a statistically homogeneous Gaussian random field. This Gaussian nature is implicitly assumed when deriving crucial cosmological parameters from the CMB temperature and polarization power spectra. However, investigating non-Gaussianity is not just about validating this assumption. It's also crucial for a better understanding of foreground residuals and systematic effects that may be present in the clean CMB map we use. Detecting non-Gaussianity, even if not primordial, can help us characterize these contaminants. The challenge with non-Gaussianity is that unlike Gaussianity, which is singularly defined, non-Gaussianity can manifest in numerous types, making its detection and quantification inherently difficult. This complexity necessitates a model-independent approach. Our solution is to implement such a method using spherical harmonic phases to investigate non-Gaussianity in CMB maps. The CMB temperature fluctuation delta T can be expressed as a sum of spherical harmonic functions with complex coefficients, ALM. These coefficients can be written in terms of their magnitude and a phase angle psi L. A key concept here is the random phase hypothesis. This hypothesis states that if the CMB temperature and anisotropies constitute a Gaussian random field, then the phases psi LM of spherical harmonic coefficients, ALM, are independent and identically distributed as a uniform distribution in the interval 0 to 2 pi. This is our null hypothesis. Any violation of this null hypothesis, either in terms of uniformity or independence of these phases, indicates the presence of non-Gaussian signals in the corresponding spherical harmonic coefficients. To test this random phase hypothesis, we design a new method using a non-parametric statistic known as Rao statistics, specifically Rao spacing test. Rao test is a powerful statistic for testing the uniformity of circular data. It's particularly effective because it's more sensitive to multimodal distributions than other common tests like the Rayleigh or Kuiper tests. Its core idea is elegantly simple. If circular variables are uniformly distributed, then successive observations should be approximately evenly spaced with an average separation of 2 pi by n, where n is the number of circular samples. Conversely, any unusually large or short spaces between observations signify non-uniformity in the set of circular variables. This makes it an ideal tool for detecting deviations from the expected uniform distribution of spherical harmonic phase. Furthermore, Rao test is a non-parametric order statistic which is invariant under the choice of origin. To elaborate slightly on the mathematical formulation of Rao statistic, given a set of n circular variable theta I in the interval 0 to 2 pi arranged in ascending order, the statistic UN is calculated as the sum of maximum of 0 and the difference between observed arc length and the expected uniform spacing 2 pi by n. If all circular variables are perfectly uniformly spaced, UN will be 0. Any deviation from perfect uniformity results in UN being greater than 0. Crucially, large values of UN indicate stronger clustering of variables and thus a significant deviation from uniformity. This characteristic makes UN a direct measure of non-uniformity, which in the context of CMB phases directly translates to a potential detection of non-Gaussianity. We use this statistic to test both uniformity and independence within and between sets of spherical harmonic phases. Our analysis applied this method to a diverse set of CMB temperature maps. First, we tested it on non-Gaussian simulations to validate its performance on maps with known statistical properties. Next, we used foreground-contaminated Planck 100 GHz and 143 GHz channel maps These are considered observed non-Gaussian maps due to the presence of foregrounds, allowing us to assess the method's ability to detect non-Gaussian signals in real complex data. Finally, we applied our method to latest Planck satellite missions. Final released clean CMB temperature and anisotropy maps, Commander, NILC, SEVA, and SPICA, along with the WMAP 9-year released ILC map. These clean maps are critical for searching for primordial non-Gaussianity. For our analysis, we extracted the spherical harmonic coefficients ALM for all these maps using the IANA fast facility in HeatPix package. From these, we derived the phase angle psi LM for multipoles ranging from L equals to 4 up to a maximum L of 128. We restricted our analysis to a maximum multipole limit of L less than 128. This choice was made because at lower multipoles, the cosmic microwave background signal dominates over noise components. By limiting our analysis to these signal-dominated regions, we avoid large contributions to the spherical harmonic phases from noise, ensuring that any detected non-uniformity or correlation is more likely to be a genuine feature of the CMB signal. Our comprehensive investigation of spherical harmonic phases involved 3 distinct classes of tests, each targeting different aspects of uniformity and correlation. Class 1 investigates uniformity of spherical harmonic phases. It has 2 types, type 1, type 2. Type 1 tests the uniformity of phases for a given L mode across all its M values. Type 2 tests the uniformity of phases for a given M mode across all its L values. Class 2 examines correlation within a given L mode, spherical harmonic phases. It has 2 types, 3 and 4. Type 3 test for correlation between consecutive M modes for a specific L. Type 4 test for correlation between next two consecutive M modes for a specific L. Finally, class 3 investigates independence of neighboring L mode spherical harmonic phases. It has 2 types, type 5 and type 6. Type 5 test for correlation between phases of consecutive L modes with the same M value. Type 6 test for correlation between phases of next two consecutive L modes with the same M value. For each of these 6 test types and for every CMB map, we use raw statistics to obtain a UN value corresponding to the test variable. To determine if an obtained UN value is anomalous, meaning it indicates a non-uniform distribution, we employ a rigorous statistical comparison. We calculated UN value for 10,000 corresponding phase sets generated from Gaussian simulations. These simulated UN values were then arranged in ascending order. A significant detection is declared if UN value obtained for the map under test is greater than 95% of the UN values obtained from the 10,000 Gaussian simulations. We also identify highly significant detections if the UN values exceed 99.9% of Gaussian simulations, corresponding to a level of 0.05 and 0.001 respectively. This approach allows us to confidently identify deviations from the expected Gaussian random field behavior. To thoroughly test the performance of our method, we developed a systematic procedure for generating Gaussian and non-Gaussian CMB maps. Gaussian CMB maps were simulated using the SyncFast facility within the HeatPix package. For non-Gaussian temperature fields, we employed a multi-step process. Instead of a standard normal distribution, we sampled random variables from 2 distinct regions, minus A to minus B and B to A, where the absolute value of A is greater than B. The values sampled from minus A minus B range were then shifted by 2B to the range minus A plus 2B and minus B plus 2B. To obtain spherical harmonic coefficient ALM, the sampled variables were multiplied by the cosmological power spectrum CL, the instrumental being DL, and pixel window function W pixel. The imaginary part of the ALM coefficient for m equals to 0 were set to 0 to ensure consistency with a real temperature field. We generated three classes of non-Gaussian simulations, non-Gaussian simulation 1, 2, and 3, with increasing deviation from a normal distribution. While our input spherical harmonic coefficients were distinctly non-Gaussian, a crucial point to understand is that because of central limit theorem, the actual signal that was presented in the spherical harmonic space gets obscured in one point statistic in the pixel space, which can be seen in the figure. The pixel value histogram for our non-Gaussian simulation closely resembles the Gaussian. This means that even if underlying ALM are non-Gaussian, the resulting pixel values being a superposition of many such coefficients tends towards a Gaussian distribution. This warrants that special care must be taken into account to study non-Gaussianity either in spherical harmonic space or pixel space, and it underscores the necessity of method like ours that directly probe the spherical harmonic phases, which retain the non-Gaussian signature more effectively. We are also here showing the mold-wise projection of one sample of these different simulations. The topmost and the leftmost is the Gaussian simulation, whereas the other ones are non-Gaussian simulation 1, 2, and 3. We do not see any visual, we do not see any non-Gaussian feature in these mold-weight projection of map. To rigorously test the performance and efficiency of our 6 test method, we performed a large-scale Monte Carlo simulation. For each of the 3 classes of non-Gaussian simulations, we generated 5,000 independent non-Gaussian realizations. We then applied all 6 of our raw statistic-based tests to each of these 5,000 simulated maps. The histogram plot indicates a small spread in the number of significant detection for each test type and every non-Gaussian map type. The light green region indicates the 1 sigma uncertainty around the mean, and it is narrow. And the small error bar around each test and set of non-Gaussian map strongly indicate that our test work efficiently and accurately in detecting significant cases. Our performance test yield highly encouraging results. As shown in the figure, for all 6 tests, the number of significant detection consistently increases, which is shown on the vertical axis, with the level of non-Gaussianity introduced in the simulations. For instance, for type 1 variable, we detected 23 significant cases in non-Gaussian simulation 1, increasing to 116 in non-Gaussian simulation 3. Compared to only 7 in Gaussian simulation. This trend is exactly what we would expect from an effective non-Gaussianity detection method. Beyond simulations, we also evaluated our method's performance on observed data that are known to contain non-Gaussian signals. The Planck foreground-contaminated 100 GHz and 143 GHz channel maps. These maps, while not clean CMB, serve as valuable test case because of the presence of foreground, whose exact statistical properties are unknown. The results summarized in the table demonstrate our method's capability. For example, for type 6 variable, we found 118 significant L mode pair in the 100 GHz map and 115 in the 143 GHz map, significantly higher than the 8 detections in Gaussian simulation. Notably, test 2, 4, and 6 proved particularly efficient in detecting these non-Gaussian signals. in the foreground contaminated Planck channel maps. This success reinforced that our method can detect non-Gaussian signals that are different from those included in non-specific simulations, further validating its robustness for real-world application. This also shows that such correlation exists in these observed non-Gaussian maps. Now let's move to the main result from the foreground minimized or clean CMB maps, which are crucial for cosmological inference. We applied all 6 tests to the commanders Nika and NILC CFMW map, ILC maps. Generally for class 1 test, which examine uniformity within L modes and M modes respectively. Phases corresponding to most of the L and M modes are consistent with random phase hypothesis. However, there are notable exceptions for type 1. L mode 57 was found significant in both commander and SME. For type 2, while no common M modes were found across all maps, modes like 79 and 113 in commander and 174, 119 in SEBA showed significant non-uniformity. For class 2 test type 3 and 4, which correlation between consecutive and next to consecutive M mode for a given L, type 3, for type 3, L mode 17, 19, 62, and 109 consistently appear as significant across multiple clean maps. For type 4, L mode 13, 14, 27, 47, and 128 were statistically significant multiple times across maps. Finally, for class 3 test, type 5 and 6 in investigating correlation between neighboring L mode for each. For type 5, examining consecutive L modes pair like 10, 11, 20, 21, 88, 88, 89, 111, 120 showed significant correlation across multiple clean maps. For type 6, concerning next to consecutive L mode, the L mode pair 12, 14 was significantly correlated across different clean maps. Overall, by looking for recurrent significance across different test types and multiple clean map, we have identified several L and M modes, L pairs that consistently violate the random phase hypothesis. This is strong evidence pointing to the presence of non-Gaussian signal in these foreground minimized maps. Thank you for your attention. I am now happy to take any question you have.